Mr. True, in this calculus lesson, we are going to go through 3 examples of integration with an integrand, which is a fraction. And it's not the first time we've integrated fractions, but it's not going to fall into one of those u over u patterns or one of those 3 inverse those rules that we learned about integrating that involves inverse trig functions. So what we're going to have to do is this technique of partial fractions. We're going to take this fractional integrand and we're going to pull it apart into pieces, undo the addition or subtraction of fractions. It's a technique that we learned, or maybe learned in pre-calculus. I do have videos for this. I'll put them in the description of the video, where you would have been learning how to solve 2 and 3 variable systems, and then extended that into this idea of partial fraction decomposition. And there's 4 cases for that. I cover them both in my full-length, very detailed pre-calculus lessons, again, listed below. But when we go through our 3 examples, the first 2 are going to have a system that's simple enough that we can go through the process of basically splitting this fraction up a lot more efficiently, a lot quicker than we did last year when we were just making sure that you understood this process of partial fraction decomposition, but we were also just, reinforcing those solving systems of equations skills that we had just got done learning. The third example, well, I don't use textbook problems in my videos. I make them up on my own, and I use a CAS calculator to help me with that. And I found a third one that I knew was going to work, and then I started working through the example and realized it had everything but the kitchen sink in it. So the third example is going to be a doozy. So our steps here, this is kind of some very technical language you'll probably see in your book. If n of x divided by d of x, or just simply numerator over denominator, is an improper fraction, which means the degree of the numerator is greater than the degree of the denominator, we're going to do that division, that's what a fraction bar means, to obtain an expression or equation where we have a polynomial plus whatever the remainder is from our division over what we're dividing by, of course. And the denominator into factors, then we're going to take the remainder over d of x, or if it's just not an improper fraction, our integrand, our fraction, we're going to factor the denominator into factors of the form p times x of q. So we're looking at x as a variable and p and q are constants, and so we're looking at we're going to factor it down until we have a bunch of factors which are linear or quadratic factors. That's what we're dealing with in our lesson. And we have p times x plus q to the m power and ax squared plus bx plus c, recognizing the standard form of a quadratic, to the n power, where x squared plus bx plus c is irreducible, which means you've just simply factored it as much as you possibly can. And a lot of times these exponents of m and n are going to be just 1, but if you have a factor that shows up twice, like you factor your polynomial, and it ends up being, x plus 2 times x plus 2, well then that's, of course, x plus 2 squared. And we're going to recognize the fact that that same linear or quadratic factor shows up more than once by, writing it with a power of 2 or 3 or so on. We'll cover that in our examples. Linear factors. For each factor of the form p times x plus q of m, I'm really just reading this kind of very technical language in the book to help you, read future sections on your own. The partial fraction decomposition must include the following sum of m fractions. So if you do have sort of like this x plus 2 squared, you're going to write a constant. A constant has a degree of 0, and we're talking about factors with a degree of 1, so we're just going to reduce that degree by 1. So linear factor, we have a constant a sub 1 over p times x plus q plus, and then a sub 2 times p times q, px plus q again, only now to the second power. So if you have a factor show up more than once, we'll say that this factor is raised to the second, the third, the fourth power, so on. But we're going to, when we expand it, say, okay, well, we have a constant over that factor to a degree of 1, some other new constant over that same linear factor or quadratic, now with a degree of 2 and degree of 3 and degree of 4 and all the way up to whatever that m happens to be. And we have the same statement here except for quadratics. Quadratic factors, for each factor of the form ax squared plus bx plus c to the n power, the partial fraction decomposition must include the following sum of n fractions. Now another thing we want to get out of here is if our factor is a quadratic, then we're going to have this idea of a linear expression above it. If our factor is a linear factor, then we'll have a constant above it. So we have b sub 1 times x plus c sub 1 over ax squared plus bx plus c. And if you have a a quadratic factor which is unique and doesn't repeat, then that's all you'll have in your expansion. But if you do have a quadratic raised to, say, a third power, then you'll have to write that denominator with that factor of the first, that factor of the second, that factor of the third, and then stop. Or whatever that factor, whatever that power, just happens to be. So this is all the fancy language. Let's get to our first example right now. For our first example, we're going to integrate 4 over x squared minus 2x minus 8 dx. And here's our integration rules, our basic integration rules that we've learned up until now that, have fractions in them. Like we have a du over u, remembering that when we take a derivative of a polynomial, we reduce that degree by 1, and we've got some square roots of a difference of squares here in the denominator, and we have a sum of squares. And we have had problems that look similar to this in our previous exercises where, we completed the square with the numerator denominator, or did something fancy here to make our integrand fit one of these integration rules. So let's try that here. We've got the indefinite integral of 4 over x squared minus 2x. Leave some room for completing the square. We're going to take a piece of orange chalk. Take half of b, divided by 2 and square it. If you add 1, of course, you have to subtract 1 to balance that out. When you complete the square, you set up a perfect square trinomial. That'd be minus. Excellent. And now you might be going, okay, well, then we've got what looks like one of these integration rules. It looks like it might be something here, but and I could say that maybe u is equal to x minus 1, and then du is equal to, if I wrote du, that it's equal to 1, and I could move the 4 up front, and we'd be okay with that. So this could be like my u prime over, or my du and my u, but and we have an a value which would be 3, but of course, I could just be quiet and just get on with it because this is not a difference of squares like we have here. This is an integration rule for a sum of squares, and it comes out to arctangent, but and some other fancy stuff in there, but we don't have a sum of squares. So this is not something that we can integrate right now using these integration rules that we know so far that involve an integrand, which is a fraction. So, partial fraction decomposition. Yep, that's what we're going to do. We're going to pull it apart. So we're going to get these formulas out of the way that we're not going to use in this example. They might come back. Hopefully I don't kick that while I'm teaching. We're going to factor the denominator. And factors of 8 that subtract 2 would be negative 4 and positive 2. And of course, that's still not, we still can't integrate this with our skills that we know so far. That's why we're learning this technique, this new section. So we're going to pull this off to the side. Go ahead and leave that original fraction in its factored form. Each of the factors in our denominator are unique, so we're not going to have to worry about that repeating issue that we had at the end of our notes there at the last screen. These are linear factors, so we're going to put some constants because that has a degree of 0, one less than a degree of 1. Great. I want to take this fraction and pull it apart and make it the sum of two fractions. I need the two sides of this equation to be equal to each other. I'm effectively setting up an identity. And what I want to do here to continue the process is multiply both sides of the equation by something that's going to get rid of these fractions and get sort of another equation without fractions in it. So we're going to multiply both sides of the equation, or the entire equation, by x minus 4 and x plus 2. And distributing this through our equation, we get 4 is equal to, when we multiply this to a, the x minus 4, of course, is going to cancel out. And now our x plus 2 is going to cancel out. And at this point, we're going to go through the rest of this now, the decomposition of this fraction, a lot quicker than we would have done in pre-calculus. And if you might be probably going back and wanting to yell at your pre-calculus teacher if they did this, because you went through a much longer process. Instead of expanding this out and setting coefficients of some particular degree terms all the way down to the constant equal to each other and make a system, which we are going to have to do for the third example, I'm going to go ahead and say, well, the two sides of this equation, they have to be equal regardless of what x is. So can I pick some x's that will allow this to kind of fall apart and let me solve for one of these variables at a time? Now I'm talking about the constants of a and b. Let's let x equal -2. If we let x equal -2, this factor is going to be 0. 0 times a is 0. And I'm going to have an equation that's just got, that's just left with b. So we have 4 is equal to, now I already said this is going to be 0. So b times -2 minus 4, that's going to be 4 equals, well, -2 minus 4 is -6. And dividing both sides by -6, we get b is equal to -4/6, which of course reduces down to, I'm going in all different kinds of directions here, -2/3. So we have a value of b. Great. Let's try and find out what a is by picking a value of x that's going to let this term become a value of 0 and sort of allow the b to cancel out. And let's let x equal 4. Well, if we do that, 4 minus 4 is 0. 0 times b is 0, so that term goes away, and we'll have a version of this equation left, or, that only has a variable of a in it. 4 plus 2 is 6. And a is going to be, after dividing by 6 and reducing, 2/3. Great. So that means that when we decompose this fraction, a couple of terms that would add up and give us this would be, I don't have to erase all this because I'm definitely going to run out of room, but we have that this is equal to a, which is, let's write over here, 2/3 over x minus 4 plus b, which is going to be -2/3 over x plus 2. Now I have these main fraction bars and I have a fraction in the numerator, and there's a couple of ways you can see how this comes apart, and you can rewrite this more simply, and I'll do that as we go through the video. But I'm going to go ahead and just remind you that when you have a fraction over a fraction, we're going to go ahead and let those denominators flip up. We'll have 2/3 times 1 over, bringing this up, x minus 4, and then minus 2/3 times 1 over x plus 2. And this is a decomposed version of this fraction. If we go ahead and take these two fractions and add them back together, finding common denominators, multiplying this by x plus 2 on the top and this numerator and denominator, and bringing x minus 4 and multiplying it to the numerator and denominator, we'll get back to the fraction that we started with. So what we're going to do is I'm going to pause the video and clean all this up, and we're going to basically, write this integrand now as 2/3 times x minus 4 minus 2/3 times x plus 2. Alrighty then. So we have decomposed our fraction. I don't really think at this point most of you are going to need to see this separated into two separate integrals, but just in case, we have our constants coming out in front of the integrals that we've now separated. If our u is x minus 4, then of course du, or u prime, is going to be just simply 1. So we have a u prime over u pattern in both of these, and so we just have 2/3 times the natural log of the absolute value of x minus 4 minus 2/3 times the natural log of the absolute value of x plus 2, and don't forget your constant of integration. Now, this is awesome, but if it's a multiple choice question, you're probably not going to see the answer in this form, so let's go ahead and factor the 2/3 out of both of these terms. And I suspect this is still not going to be the form that you see your answer, but of course, logarithms are exponents, and when do you subtract exponents? When you divide like bases. So this is going to come out to be as our final answer, 2/3 times the natural log of x minus 4 over x plus 2 plus c. And that is the end of our first example. Next one coming up right now. Bam! Now our second example. We're going to do the indefinite integral of 4x cubed minus x plus 1 over 2x squared minus 3x minus 2. And this isn't the first time we've tried to integrate a fractional radicand or integrand that has a numerator whose degree is larger than the denominator. We just, an improper fraction. We just have to remember to go through the long division process to break this up into a polynomial plus the remainder over what we're dividing by, which I'm pretty sure you remember how to do long division. Great. So that means that we're looking at integrating. Whoops. Said I was going to kick that eventually. We're going to integrate. Here's what our sort of answer is from the division. 2x plus 3, our polynomial that we were looking for, plus the remainder over what we're dividing by. Now, this portion of our integrand obviously is going to be very easy to integrate. It's all about now dealing with the second, or the fractional part of our integrand. So let me go ahead and pull this apart. And this is really why I wanted to talk about this example, just to show you what you have to do if you have an improper integrand. The rest of this process for integrating this 12x plus 7 over 2x squared minus 3x minus 2 will follow the exact same pattern that we just did in our previous example. So I'm going to step off, reveal the solution one step at a time. It's a good time for you to, I would suggest pausing the video and trying this on your own and making sure you have the same answer that I do. Bam! Last example, and it's going to be the indefinite integral of x squared plus 2x plus 3 over x to the fourth plus 4x squared plus 4 dx. And let's see here. We have a numerator whose degree is smaller than the denominator, so we don't have an improper fraction. And so let's go ahead and get this denominator factored out. We're going to have the indefinite integral of x squared plus 2x plus 3 all over. Okay, we have a power of 4, but this is a power of 2, and then we have a constant, so this is just sort of another version of a quadratic here. We have a leading coefficient of 1, factors of 4 that add up to 4 is 2. So we have x squared plus 2. And it is, the factors of 4 that do add up to 4 is 2 and 2. So we're going to have that same factor show up twice. Awesome. And we're not going to fit this entire problem on the board all at once, so we'll have to kind of pause and clean the video up and or the chalkboard up as we go and all that good stuff. So we're going to have, let's see here, we have a function inside the power of 2, and you might go, well, maybe u is equal to x squared plus 2, but then du is equal to x, which is a single degree function, and we have a second degree in the numerator, and of course it just is not going to work. So let's do some partial fraction decomposition, and we're going to have x squared plus 2x plus 3 over x squared plus 2 to the second power. We're going to recognize, and I guess our notes would have said this is in the form of, you know, ax squared plus bx plus c. There's no x because b is equal to 0. And we're supposed to, if our factors are quadratics, write linear functions in the numerator. So the first time we're seeing that. So ax plus b over x squared plus 2. And this is also the first time we're seeing that we have a factor that's repeating. So we're writing that x squared plus 2 to the first power, and now we're going to do it to the second power with another linear function in the numerator with a bunch of unknown constants. Great. Well, still like before, we're going to multiply this entire equation by something that cancels out all of the denominators, which of course is just going to be x squared plus 2 squared. Okay, I don't really know why I'm writing that in a set of parentheses, but we do need the parentheses here because what's going to happen is multiplying by x squared plus 2 squared, of course that's going to cancel out with our first term, just leaving us with the numerator. With our second term here, we have one of those x squared plus 2's, so that's going to cancel out with one of these two and leave us with a multiplication of that in the numerator. And then finally here, that's going to completely cancel out, and we just have cx plus d. Now, unlike the first two examples, trying to figure out what the constants of a, b, c, and d are going to need to take us back to that video that I did for my pre-calculus lessons, or for you all out on YouTube, which is we're going to have to expand the right-hand side and actually create a systems of equations, because we're not going to be able to just pick you know, some value of x that's going to allow all these variables of a, b, c, and d to cancel out except for one of them. So let's get this expanded and start matching up the coefficients of, well, whatever powers we have up. We're going to end up with a power of 3, 2, and 1, and then some constants, and we'll match all those up and get a systems of equation going. Okay, now let's see here. We have some third degree, second degree, first degree terms in our 2b plus d. So I'm just going to reorganize this stuff. Okay, now what I also want to do is I'm going to, just for, well, I can make a new line. We're going to factor the x's out of here. And we're going to have, here's my notes taking up a whole page because I like to show all of my steps for me and for you guys out there learning. I just want to make sure I'm not writing something incorrect because I'm unfortunately prone to making small mistakes, even now as a teacher, and apparently I lost a 2b somewhere. Ah, good thing I checked. All right. I can see my students' mistakes immediately when they're usually when they're asking questions, but for some reason it's always harder to find your own. So I prep my notes really well for these videos. And 2 plus acx, 2b plus d. Awesome. Now, we're going to match up here. What we do with these systems of equations is we go, okay, we have powers of 2, 1, and constants. Over here on the right-hand side, we have powers of 3, 2, 1, and we're going to match up the coefficients of all of these degrees. Well, there is no power of 3 on the left-hand side, which means that, well, if we say that there's some kind of variable of x to the third power, then its coefficient would have to be 0. So we have a is equal to 0, and now matching up the coefficients of our second degree terms, we have only 1 second degree term on the left and 1 degree of 2 on the right, so b is going to be equal to 1. Now looking at our, maybe pick some different colors here. Now picking our coefficients of our single degree term, we have 2 is equal to 2a plus c, but thankfully, as nasty this was starting to look, the system of equations we have here actually, thankfully, comes out pretty simple, easier than most of the ones in my pre-calculus lesson. And we already know that a is equal to 0. So if we have 2 times 0, then c is just going to be equal to 2. And now finally, we have to match up our constants. And we've got 3 is equal to 2b plus d. And we already had a value of b, it's equal to 1. So now we're looking at 3 is equal to 2 times 1 plus d. So we have, oh, well, yes, and then of course, d is equal to 1. So with our values of a, b, c, and d, easy as, never mind, I can't sing the whole thing. That is a copyrighted song. So this is going to be equal to ax plus b, or a0 x plus b, which is 1 over x squared plus 2, plus, we got cx, and c is 2, so 2x plus d, which is 1, over x squared plus 2 squared. Now, what that means is we're going to come over here and rewrite our integral as the indefinite integral of, well, all of this is equal to 1 over x squared plus 2 plus 2x plus 1 over x squared plus 2 squared dx. And we're going to pull this apart in small little integrals like I've been doing to hopefully help your understanding as much as possible. Now over here we have 1 over x squared plus 2. So we have a constant over a sum of what is going to be a sum of squares. So this is going to end up working into some kind of, well, if my u is x squared plus 2, my du would be 2x. Okay, so it's not u prime over u. It's got to be one of those inverse, those integrals involving inverse trig functions. But over here, if I have a u, which is x squared plus 2, then my du, like we talked about this u substitution with integrating and how it's something related to that old chain rule from long ago, we get 2x dx. Okay, now look at my numerator. I have a 2x in my numerator. So if I pull this apart to be two separate fractions and have it as 2x over x plus 2 squared, and then plus 1 over this, then I'm going to have one term that is pretty easily integrated because it's just going to be u prime over u. Awesome. So we have an integrand, an integral that's going to end up being some inverse trig function, arctangent. We're going to have a u prime over u, that's going to be the natural log of something. And now we have the integral of 1 over x squared plus 2 squared. Well, that kind of looks like the same as what we have over here, but here our x squared plus 2 is inside a power of 2. Okay, so we've already explained how this isn't u and u prime, and it's not simply some kind of du over, a squared plus u squared, so it can't be just a simple arc tangent. And if this doesn't follow one of those integration rules for inverse trig functions, then it must be, if we can integrate it, something that we can work out using some trigonometric substitution. And sides of a right triangle, we just got done doing that lesson, would be some kind of square root of a sum of squares when that was going to describe the length of a hypotenuse, and a square root of a difference of squares if we have some kind of expression describing the length of a leg of a right triangle. So if we rewrite this as the indefinite integral of 1 over, now let's get this inside a square root symbol, x squared plus 2 squared. Now, square roots and squares together, square root in a square acts as an absolute value function, but x squared plus 2, that's going to be a positive value anyway, so we don't have any issues there. So rewriting this as the square root of x squared plus 2 squared, and then having that also to a power of 2, means that we can have a situation here where it's the indefinite integral of 1 over the square root of x squared plus 2 raised to the 4th power dx. Now, I'm obviously going to run out of room, and plus I'm focusing on just this part to let you see the direction that we're going in, which means I'm going to step off, clean all this up, start setting up a diagram to help us with this trigonometric substitution. Hopefully you're comfortable with that now, and understand that we have a square root of x squared plus 2. We have a sum of squares, basically. So this is going to be describing the length of the hypotenuse of our little right triangle as we set up a diagram to help us with that trig substitution. With all that cleaned up, we now have, again, this requirement that we're going to need to do a little bit of trigonometric substitution. We're going to set up a measure of theta, or a diagram to help us figure this out, with theta in this lower right-hand corner. And with this square root of a sum of squares, like I said, we're describing the length of a hypotenuse. So here we go with our square root of x squared plus 2. And that is going to mean that our value of u is going to be equal to x, and a is going to be equal to the square root of 2, because it's, some function squared plus a constant squared. Now, when set up our trigonometric substitution, just in case you need a refresher or just to kind of continue to solidify this with your own understanding, we want to set up a trig function, a primary trig function of theta, a primary trig function sine, tangent, or secant. So we are going to also want our constant in the denominator. So we're going to go ahead and let this vertical leg be our x, and the horizontal leg be our square root of 2, so that we have the tangent of theta is equal to x over the square root of 2. Moving the square root of 2 over with multiplication, we get x is equal to the square root of 2 tangent of theta. Dx is going to be equal to the square root of 2 times the derivative of tangent of secant squared theta. And what is that going to get rid of here? That's going to take care of our dx, and we're going to need a substitution to deal with the square root, or with the radical. So we have, let's see here. Again, we want to use a trig function here. We want to have our constant be our denominator. So we have our hypotenuse over the adjacent, or r over x if we're talking about angles in standard position, and that is going to be secant. So we have the secant of theta is equal to the square root of x squared plus 2 over the square root of 2. And so the square root of x squared plus 2 is equal to the square root of 2 secant theta. Now, and I'm going to just keep copying these first two terms with their integrals as we go along, and not have to worry about the constant of integration. And we're going to have, therefore, plus the indefinite integral. Dx was the square root of 2 d theta. And our square root of x squared plus 2 is the square root 2 secant of x raised to the 4th power. Let me just copy this down. Okay. Now, if we raise this to a 4th power, and I'm going to not burn an entire line for this, square root of 2 times square root of 2 is 2, but we're doing that twice, so we're looking at basically 2 times 2 is 4 times secant to the 4th power. Now we have secant to the 2nd power on top, and in the denominator we have secant to the 4th. So of course 2 of those are going to cancel out. And we have 1 over secant squared now. There's no other trig functions left, so let's go ahead and write 1 over secant as cosine. Okay, now this looks like a pretty easy integral, except inside my power of 2 I have a cosine. If I let u be cosine, there's no du, so we're going to use a power reducing formula to expand that, and that's going to be cosine squared of theta is 1 plus cosine of 2 theta over 2. And the integral of cosine is sine, because the derivative of sine is cosine. And now that I've finished all this integration, don't forget about your constant of integration. Now, just to make sure I didn't write something silly, we do have 1 over the square root of 2 arc tangent of x over the square root of 2 minus x squared plus 2 to the negative 1 negative 1 power plus square root of 2 over 8 theta plus, and we've got a 1/4. Now, what did I do wrong there? You know, this is when I pause the video and I'm not thinking about where I'm going and I write one line at a time and I use my notes ahead of time, then, you know, I do make fewer mistakes. But so now do I show you that I'm human? Do I show you like some issues that students as well get tripped up on, or do I pretend like I never make any mistakes? Well, of course, that's just not true. And nobody does this work without making any mistakes. So what is going on? Well, when we pull this apart, it's the square root of 2 over 4 times all of this. And then I didn't include any parentheses. So it was this times the 1 integral. Well, then I pulled it apart. So at that point, I needed to have wrote or included a set of brackets there. So okay, let's try this again. So when we have that square, I just want to make sure I didn't make any small mistakes and then carry it through to the end and let you guys have a flawed lesson. We have the square root of 2 over 4 times the indefinite integral of, you know, basically what was one term, 1 plus the cosine of 2 theta over 2. But we separated that. We wrote 2 separate integrals, and yes, I forgot to carry that, either carry the square root of 2 over 4 to each of those integrals or wrap the whole thing in a set of parentheses. So I got gotten a little bit of a pickle there. But still, we have our inside function. The derivative of 2 theta is equal to 2. Introduce multiplication of 2 in the numerator. Got to balance it out in the denominator. 2 times 2 is 4. 4 times 4 is 16. And the integral, of course, of cosine is sine. All right. Now, we got all that cleared up. And don't have any small mistakes, I believe now. And now we're going to get back up our board with our relationship between x and theta, and let's get this thing finished and remove the references of theta because they weren't in the original problem. So we're looking at 1 over the square root of 2 arc tangent of x over the square root of 2 minus 1 over x squared plus 2, of course just getting rid of that negative exponent. We have plus, not quite done yet, because here we have the sine of 2 theta, but all of our references, our little equations relating x and theta together, don't have a double angle in them. So this is going to be, let's try this again, working on the fly. The sine of 2 theta is 2 times the sine of theta cosine of theta. And the 2 and the 16 are going to cancel that out, giving us a new denominator of 8. So we're looking at square root of 2 over 8 times the cosine of theta, cosine of theta. All right, we have square root of 2 over 8. We need a replacement for theta, and we don't have one of those yet. So, but here we can say, well, if the tangent of theta is equal to x over the square root of 2, then theta is going to be equal to the inverse tangent, or arctangent, of x over the square root of 2. Had one of those over here as well. So we have the square root of 2 over 8 times the arctangent of x over the square root of 2 plus square root of 2 over 8. Now the sine of theta is equal to, sine of theta is equal to opposite over hypotenuse, so x over the square root of x squared plus 2. And the cosine of theta is the square root of 2 over this. And almost ran out for my room for my constant of integration. Okay, now let's see here. We've got an arctan here, we've got an arctan here. Rationalizing this denominator, we're going to have the square root of 2 over 2. This has a denominator of 8, so a common denominator is coming in here and multiplying the numerator and denominator by 4. And we have 4 square root of 2 plus, well, I guess I could just add that. We have common denominators, and we have, well, square roots of 2. So we have 4 square root of 2 plus square root of 2, which is 5 square root of 2 over 8, or this, 5 square root of 2 over 8. Now I'm going to doubt everything I say. Arctan of x over the square root of 2 minus 1 over x squared plus 2. Here we have the square root of 2 times the square root of 2 is 2x. And of course the 2 is going to cancel out with 8 here in a minute. We have 8, and the square root of x squared plus 2 times the square root of x squared plus 2 is just going to be x squared plus 2 plus c. Here we have, of course, the 2 and the 8 canceling us, giving us 4. And just to make sure we're finishing this off correctly, we have 5 square root of 2 over 8 arctan x over the square root of x, and then plus, now we have some no real reason to put this together, but just to make the end of my problem match my notes, we have easily found common denominators here. We can come in here and multiply this by the 4 in the numerator and denominator and write 5 square root of 2 over 8 arc tangent of x over the square root of 2. Common denominator, so we're going to be talking about plus, what do we have here? X minus 4 over 4 times x squared plus 2 plus c, and that is the end of our third example. Hopefully these three together allow you to do all the mechanical problems, most of your work involving integrating that involves partial fractions, and the title used to be up there. At any rate, I'm Mr. True. Bam! Go do your homework.